Hello everyone, and welcome to today's session. I am Priyanka A, and I'll be guiding you through our topic for today. The focus of our presentation is Overview of Object-Oriented Programming. We'll explore what OOP is, its core concepts, and how it's used in software development. So, let's dive in and get a clear understanding of this fundamental programming paradigm. Thank you for being here, and I look forward to our discussion. Object-Oriented Programming, or OOP, is a programming paradigm that revolves around the concept of objects. These objects are essentially instances of classes, which serve as templates for creating them. When designing applications or computer programs, this approach helps organize code more intuitively. What makes OOP powerful is that it focuses on two main aspects: data, which we often call attributes, and behavior, known as methods. These are bundled together within objects, creating a neat package. By doing this, OOP promotes modularity, meaning your code is broken into manageable, self-contained pieces. It also encourages reusability, so you can use the same objects or classes across different parts of your project, saving you time and effort. And of course, it enhances maintainability, making your code easier to update and troubleshoot later on. Throughout this presentation, you'll see how these core principles of OOP help you develop more efficient, scalable, and understandable software. Let's take a closer look at how object-oriented programming, or OOP, compares to other programming paradigms. On this slide, you can see we're highlighting OOP versus POP, which stands for Procedural-Oriented Programming, and OOP versus FOP, which is Functional-Oriented Programming. When we talk about OOP versus POP, the main difference is how we organize and manage code. POP tends to focus on a sequence of procedures or routines, which are executed step by step. It's very linear and straightforward, but can become cumbersome as projects grow larger. In contrast, OOP organizes code around objects. Think of these as real-world entities that encapsulate data and behaviors. This makes it easier to manage complex systems, promote reusability, and improve maintainability. Now, comparing OOP with FOP, the key difference lies in their approach to handling data and functions. FOP emphasizes pure functions and immutability, leading to code that's often more predictable and easier to test. OOP, on the other hand, focuses on objects that combine data and methods, which can be more intuitive when modeling real-world scenarios. Throughout this presentation, understanding these paradigms helps us see why OOP has become so popular. It's flexible, modular, and aligns well with how we naturally think about entities and their interactions. Ultimately, choosing the right paradigm depends on the problem at hand, but knowing these differences gives us a solid foundation for making those decisions. Let's take a closer look at FOP versus OOP. These are two fundamental programming paradigms that shape how we write and organize our code. First, with FOP, or functional programming, the focus is on pure functions, avoiding shared state and mutable data. It emphasizes immutability and stateless functions, which can make your code more predictable and easier to test. On the other hand, OOP, or object-oriented programming, organizes code around objects. Think of them as real-world entities that bundle data and behavior together. This approach promotes concepts like inheritance, encapsulation, and polymorphism, making it easier to model complex systems. Throughout this presentation, we'll see how these paradigms influence design choices and how understanding their differences helps us write more effective code. So essentially, FOP is all about functions and statelessness, while OOP centers around objects and their interactions. Both have their strengths, and knowing when to use each is key to becoming a versatile programmer. Let's take a closer look at the basic components of object-oriented programming, or OOPs. These components are the building blocks that make OOPs so powerful and flexible. First, we have classes. Think of classes as blueprints or templates for creating objects. They define the attributes and behaviors that the objects will have. Next, we have objects themselves, which are instances of these classes. Objects represent real-world entities, like a specific car or a person, with their own unique data. Another key component is encapsulation, which is about bundling data and methods together and hiding the internal details from outside interference. This helps us protect the integrity of the data. Then, there's inheritance, a feature that allows a new class to derive properties and behaviors from an existing class. This promotes code reuse and helps us create more specialized classes. Lastly, polymorphism enables us to treat objects of different classes through a common interface, making our code more flexible and easier to extend. Understanding these core components helps us appreciate how OOPS allows us to write modular, maintainable, and scalable code. It ties everything together by emphasizing the importance of designing software that closely models real-world systems. A class represents a set of objects that share a common structure and behavior. Think of it like a blueprint or a design prototype that defines what those objects will be like. Essentially, a class describes a common type, including properties. Those are the attributes or data and methods, which are the functions that operate on those properties. Once we have a class defined, we can create instances of it, which we call objects. These objects are specific examples of the class, each with their own unique data, but following the same structure and behavior outlined by the class. This concept is fundamental because it helps us organize and model real-world entities in a clear and systematic way, tying into the overall theme of understanding how objects and classes work together in programming. Let's take a closer look at behavior in the context of classes. Behavior primarily refers to member functions, also known as methods, which define what an object can do. These methods are the actions or operations that an object performs, and they help us understand how objects interact within a program. Moving on, the concept of a class can be thought of as a combination of state and behavior. The state represents the current data or condition of an object, while the behavior defines what the object can do with that data. Focusing on state, this is captured by data members, which are the variables that hold the object's information. These data members can also be called fields or properties, and they define the attributes of an object. Together, data members and methods form the foundation of object-oriented programming, enabling us to model real-world entities effectively. Remember, understanding how state and behavior work together is key to designing good classes and, ultimately, robust applications. Now, let's take a closer look at objects, which are fundamental to understanding Java programming. An object typically has three key aspects: its state, its behavior, and its identity. The state refers to the properties or attributes that describe the object at a specific moment in time. Think of it as the current condition or characteristics of the object. Behavior, on the other hand, is represented by methods. These methods define what an object can do, how it acts, and also how it communicates with other objects. They are like the functions or actions that the object can perform. Then there's the concept of identity. Every object needs a way to be uniquely identified, and we do this by giving it a distinct name. This helps us distinguish one object from another, especially when managing multiple instances. It's important to remember that an object is a representation of a real-world entity. In Java, we say an object is an instance of a class. A class acts like a blueprint. It defines the structure and behavior, and from that blueprint, we can create many objects. These objects don't exist in isolation. They often communicate with each other by passing messages through methods. This interaction is what makes the object-oriented approach so powerful and flexible, enabling us to model complex systems more intuitively. Hello, everyone. Today, I want to talk about Priyanka Arunachalam, who is a key figure in our discussion. Priyanka has made significant contributions in her field, and her work embodies many of the core themes we've been exploring throughout this presentation. Her approach is innovative and collaborative, emphasizing the importance of combining technical expertise with a deep understanding of community needs. By highlighting her journey, I hope to illustrate how dedication and a holistic perspective can lead to impactful solutions. Priyanka's story is a great example of how individual efforts can align with larger goals, inspiring us all to think creatively and act purposefully. Objects in the real world are all around us, and understanding them is fundamental to how we interact with our environment. When we talk about objects, we're referring to tangible things that we can perceive through our senses, things like chairs, cars, or even natural elements like trees and rocks. Recognizing these objects is a key part of many AI applications, from robotics to computer vision. What's interesting is that these objects aren't just isolated items. They have properties, relationships, and contexts that give them meaning. For example, a cup might be on a table, and the table might be in a kitchen. Connecting these objects to their surroundings helps us create a more comprehensive understanding of the world. This concept ties back to our overall theme of how machines perceive and interpret their environment. By teaching machines to recognize objects as they exist in the real world, we're enabling smarter, more intuitive systems. So, grasping the nature of objects in the real world is a crucial step toward more advanced perception technologies. Hello, everyone. Today I want to introduce Priyanka Arunachalam, a key contributor to this project. Priyanka's expertise and insights have been instrumental in shaping our approach and driving results. Her work exemplifies the importance of collaboration and innovation in achieving our goals. As we move forward, keep in mind how diverse perspectives like hers continue to strengthen our overall strategy and help us address complex challenges. Priyanka's dedication reminds us that success often comes from the collective effort of talented individuals working together. All right, let's take a closer look at the anatomy of a class. When we talk about a class, it essentially acts as a blueprint for creating objects, and understanding its structure is key. On one side, we have the private members, which include data and functions that are hidden from outside access. These are the internal details that help maintain the integrity of the object. Then we have the public members, specifically the public interface of the class, which are accessible from outside and used to interact with the object. Within this public interface, you'll find functions like run, fly, or pop. These represent the behaviors or actions that the object can perform. Moving inside the class, there are also special functions such as constructors and destructors. Constructors are responsible for initializing objects when they are created, while destructors clean up resources when objects are no longer needed. Additionally, there are ADT functions, like run, fly, or pop, that define the core operations related to the class's purpose. Private functions, on the other hand, are used internally to support the class's operations, but are not exposed to the outside world. All of this together forms the complete structure of a class, highlighting how data and functions are organized to create a robust, encapsulated design. This understanding is fundamental as we move forward to see how classes enable us to write modular, efficient, and maintainable code. Let's talk about data abstraction. Essentially, it's about exposing only the essential parts of an application that are necessary for the user to interact with. For example, think of a car. When you use a car, you're not concerned with all the internal components like the engine or the transmission. Instead, you just see and use the car as a whole. Similarly, in software, abstraction allows us to hide complex details and present only what the user needs to see and interact with. This helps simplify interactions and makes the system more user-friendly. So, abstraction is all about focusing on what really matters and hiding the complexity behind the scenes, which is a key concept in designing effective applications. In Java, abstraction is mainly achieved through interfaces and abstract classes, and interestingly, we can achieve full 100% abstraction just by using interfaces. The main idea here is that abstraction helps bridge the gap between what the user intends to do and what actually happens behind the scenes in the system. It makes technology more accessible and easier to use. For example, when you press a button on your remote, you don't need to worry about the infrared protocols or the circuits inside the TV. All that complexity is hidden from you. You simply press a button and the TV turns on. That's the power of abstraction. We can think of abstraction as existing at different levels. At a high level, it's very user-friendly, like just press power button. But at a lower level, it involves binary signals and complex electronics that operate the hardware. So, The abstraction layers protect us from the technical details, making systems easier to interact with without needing to understand every underlying process. This concept is fundamental in programming because it allows us to focus on what the system does, rather than how every component works internally. It's a key part of making technology both powerful and user-friendly. Advantages of abstraction are quite significant when we think about designing and developing applications. First, it helps to reduce the complexity of viewing things. By hiding unnecessary details, it makes it easier for us to understand and work with the system. This way, we can focus on what's truly important without getting bogged down by the underlying intricacies. Additionally, abstraction avoids code duplication and increases reusability. When we create abstracted components or modules, we can reuse them across different parts of the application, saving time and effort. This not only makes development more efficient, but also helps maintain consistency. Another key benefit is security. Abstraction helps enhance the security of an application because only the essential details are exposed to the user. Sensitive or complex internal workings are hidden away, making it harder for external users to tamper with or access critical data. Moreover, abstraction improves the maintainability of the application. When the internal system is well abstracted, making updates or fixing bugs becomes much easier. We can change internal details without impacting the end-user experience, which is crucial for long-term stability. It also boosts the modularity of the application. By breaking down the system into manageable, independent modules, each with a clear purpose, we can develop, test, and update parts of the system more efficiently. Finally, because of this modularity and abstraction, any enhancements or changes become much easier to implement. We can perform these updates internally without affecting the end users, ensuring a seamless experience. This flexibility is vital for keeping our applications robust and adaptable over time. Let's take a closer look at the code and its output. In this program, we have an abstract class called PetAnimals. This class contains an abstract method named AnimalSound, which means that any subclass must provide its own implementation of this method. Next, we create a dog class that inherits from PetAnimals. In the dog class, we override the AnimalSound method to specify what sound a dog makes. This highlights the concept of abstraction, defining a general idea in the base class and then customizing it in the subclasses. By doing this, we see how inheritance and method overriding work together to enable polymorphism, allowing us to treat different animal objects uniformly while still customizing their specific behaviors. This example ties into our overall theme of understanding object-oriented programming principles, especially how abstract classes and method overriding facilitate flexible and maintainable code. Now, let's take a closer look at encapsulation. Encapsulation is a fundamental concept in object-oriented programming that helps us protect data and maintain a clear structure in our code. It involves wrapping data and the methods that operate on that data within a single unit or class and restricting direct access to some of the object's components. This way, we control how the data is accessed or modified, which enhances security and reduces the risk of unintended side effects. To illustrate this, I'll share an example from Priyanka Arunachalam, which demonstrates how encapsulation is implemented in practice. The key takeaway here is that by encapsulating data, we create more robust, maintainable, and secure applications. It's a core principle that aligns with our overall goal of writing clean, efficient, and reliable code. Let's talk about encapsulation. Encapsulation is all about hiding or protecting data, which is a fundamental concept in programming. When we achieve encapsulation, we're essentially wrapping data and the methods that operate on that data into a single unit. This helps us control how the data is accessed and modified. Now, according to Priyanka Arunachalam, the first law of object-oriented programming is that data must be hidden, meaning it should be private. To access this data, we use read functions for reading and write functions for modifying it. For each piece of data, there are 4 possible scenarios. First, both read and write are allowed, giving full access. Second, only read access is permitted, so the data can be viewed but not changed. Third, only write access is granted, meaning the data can be modified but not directly viewed. And finally, no access at all, keeping the data completely protected. Understanding these access possibilities is crucial because they help us enforce data security and integrity within our programs. Encapsulation, through these access controls, ultimately helps us build more robust and maintainable software. Proper encapsulation is a fundamental concept in object-oriented programming, and it can be effectively achieved by making our data members private. This means that the internal state of an object is hidden from outside entities, helping us protect the integrity of the data. At the same time, we make the methods that operate on this data public. These public methods act as controlled interfaces, allowing external code to interact with the data in a safe and predictable way. By doing this, we ensure that the data is completely protected from unintended or malicious access, which is crucial for maintaining the robustness of our programs. This approach aligns perfectly with the overall theme of creating secure, maintainable, and well-structured code. Proper encapsulation not only safeguards data, but also makes our code more modular and easier to manage in the long run. In this slide, we're looking at a program that features a class called Customer Account. Now, within this class, all the data members are declared as private, which is a crucial point. This means that these fields cannot be accessed directly from outside the class, helping us safeguard the data. To interact with these private fields, we provide public methods called getters and setters. The getters allow us to read or retrieve the values, while the setters let us modify or set new values. This setup is a perfect example of encapsulation, which we've discussed earlier. Encapsulation helps us hide the internal details of the class and control how data is accessed or changed. By doing this, we prevent external code from making unintended modifications, ensuring data integrity. The slide also shows the output, which is the name Priyanka Arunachalam, demonstrating how the getter methods work to access data safely. Overall, this approach emphasizes the importance of protecting data and controlling access through well-defined methods, which is a core principle of object-oriented programming. Inheritance is a fundamental principle in object-oriented programming that allows us to create a new class, often called a child or subclass, by inheriting attributes, methods, and behaviors from an existing class, which we refer to as the parent or superclass. This concept is powerful because it establishes a relationship. For example, we can say a car is a vehicle, which means that the car class inherits general characteristics from the vehicle class. This setup not only promotes code reuse, but it also helps us organize our code into hierarchies, making it more manageable and easier to extend over time. Instead of duplicating code, we can build on existing classes and add specific features as needed. In the context of our overall discussion on object-oriented principles, inheritance is a key mechanism that underpins how we design flexible, reusable, and maintainable software systems. It enables us to model real-world relationships more naturally, which is essential for creating intuitive and efficient programs. Now, let's take a closer look at some key concepts related to inheritance and interfaces. First, the extends keyword is used for single inheritance. This means that a child class inherits from just one parent class. For example, if we have a class car that extends vehicle, the car inherits properties and methods from vehicle. This helps us build specialized classes based on more general ones. Next, when we talk about the implements keyword, it's used with interfaces. Interfaces define contracts that classes agree to fulfill. A class can implement multiple interfaces, allowing it to adhere to different sets of behaviors. For instance, if a class car implements runnable, it promises to provide the behavior defined by the runnable interface. Moving on to non-private members, it's important to remember that child classes inherit public and protected fields and methods. However, private members are not directly accessible in subclasses. To access private data, it's common to use getters and setters, which encapsulate the private fields safely. Finally, the parent-child relationship is fundamental. The superclass provides a base set of features, and the subclass can add new features or override existing ones. For example, a subclass might override a method to provide specialized behavior, which helps us create more specific classes while reusing existing code. Throughout all of this, keep in mind that understanding how inheritance and interfaces work together is key to designing flexible and maintainable object-oriented systems. Today, I want to highlight the incredible work of Priyanka Arunachalam. She's a key figure in our project, and her contributions have been vital. What really stands out about Priyanka is her dedication to innovation and her ability to bridge complex concepts with practical solutions. Her expertise not only pushes our project forward, but also inspires the entire team to think more creatively. As we've seen throughout this presentation, success often hinges on the collaboration and diverse perspectives that people like Priyanka bring to the table. So, her role exemplifies the importance of teamwork, expertise, and a forward-thinking mindset in achieving our overall goals. Priyanka Arunachalam. Today, I want to highlight her contributions and insights, which are really integral to understanding the broader context of our presentation. Her work exemplifies the innovative approaches we're discussing and demonstrates how individual expertise can drive meaningful change. By focusing on her key points, we see how her strategies align with our overall theme of progress and transformation. It's important to recognize how her efforts connect to our goals of fostering collaboration and advancing knowledge in this field. Her perspective reminds us that impactful change often starts with dedicated individuals who are willing to think differently. So, as we move forward, keep in mind how her example can inspire us to adopt similar innovative mindsets. Let's take a look at an example of an ISA relationship. On this slide, you'll see how this type of relationship works in practice. The key idea here is that an ISA relationship describes how one class or entity is a specialized version of another. For instance, if we have a class called vehicle, then car is a vehicle. This means that a car inherits the properties and behaviors of a vehicle, but also has its own specific features. Highlighting this relationship helps us understand how inheritance structures are built in object-oriented design. By grasping ISA relationships, we're better equipped to model real-world scenarios more accurately and efficiently. Remember, this concept underpins much of the way we organize and reuse code, making our systems more modular and easier to maintain. Hi, I'm Priyanka Arunachalam, and I want to take a moment to highlight some key points that tie into our overall theme. Throughout this presentation, we've explored various strategies and insights, and I believe these elements are crucial for our success. As we discuss these ideas, keep in mind how they connect to the bigger picture, improving efficiency, fostering innovation, and driving growth. My goal is to share these concepts in a way that's clear and engaging, so we can all leave with a better understanding of how to move forward effectively. Access control keywords are essential because they help us define which classes can access other classes, methods, and members. Essentially, they set the rules for how different parts of our code can interact with each other. By using these keywords, we can control the visibility and accessibility of various components, which is crucial for maintaining encapsulation and ensuring our code remains secure and well-structured. This ties into the overall theme of designing robust and modular software, where controlling access properly helps prevent unintended interactions and keeps our codebase manageable. Today, I want to highlight a key design choice in object-oriented programming: avoiding multiple class inheritance. One of the main reasons for this is to prevent the diamond problem, which can occur when a class inherits from two classes that share a common ancestor. This situation can lead to ambiguity and confusion about which inherited properties or methods to prioritize. Instead of multiple inheritance, we often use interfaces. Interfaces allow us to define a contract that classes can implement, ensuring flexibility without the complications that come with inheriting from multiple classes. Now, moving on to the types of inheritance, it's important to understand the different ways classes can relate to each other. Inheritance helps us promote code reuse and establish hierarchical relationships between classes. These relationships can be simple, like a subclass inheriting from a superclass, but they can also get more complex. Recognizing the different inheritance types helps us design more robust and maintainable systems, aligning with our overall goal of creating clear, efficient, and scalable code. Let's dive into the concept of polymorphism. Polymorphism is a fundamental principle in object-oriented programming that allows objects of different classes to be treated as instances of a common superclass. Essentially, it enables us to write code that can work with objects of various types through a shared interface. This is incredibly powerful because it promotes flexibility and reusability in our code. For example, imagine we have a base class called animal and subclasses like dog and cat. Polymorphism allows us to call a method like makeSound on an animal reference, and at runtime, the correct subclass method, whether it's barking or meowing, will be executed. This dynamic behavior is what makes polymorphism such a key feature. Connecting this to our overall theme, polymorphism helps us design systems that are more modular and adaptable. It simplifies maintenance and extension because new classes can be added with minimal changes to existing code. So, understanding and leveraging polymorphism is vital for creating robust, scalable software solutions. Polymorphism, which comes from the Greek word meaning many forms, is a fundamental principle in object-oriented programming. It allows objects of different classes to be treated as instances of a common superclass or interface. This means that even if objects belong to different classes, they can still be handled in a uniform way, as long as they share a common interface. One of the most powerful aspects of polymorphism is that it enables the same method name to perform different actions depending on the object that calls it. This flexibility allows us to write more extensible and maintainable code because we can add new classes without changing existing code. Overall, polymorphism helps us design systems that are more adaptable and easier to extend, which ties back to our broader theme of creating robust and scalable applications. Priyanka Arunachalam. Today, I want to highlight her contributions and impact. Priyanka has been a remarkable figure in her field, showcasing dedication and innovative thinking. Her work exemplifies how passion combined with expertise can drive meaningful change. Throughout her career, she has consistently pushed boundaries and challenged the status quo. This aligns perfectly with our overall theme of innovation and leadership. By understanding her journey, we can gain insights into how perseverance and creativity lead to success. Her story encourages us all to pursue our goals with determination and a forward-thinking mindset. So, let's take inspiration from her achievements as we continue to explore the broader landscape of change and growth. Now, let's talk about runtime polymorphism in Java, which is also known as dynamic method dispatch. This is a key concept because it allows the program to decide at runtime which method to execute, especially when dealing with inheritance and method overriding. Essentially, when you call an overridden method, Java determines which version of that method to run during execution, not at compile time. This dynamic resolution is what makes your programs more flexible and adaptable. This process is achieved through method overriding. To clarify, method overriding happens when a subclass provides its own version of a method that already exists in the base class. The base class method is said to be overridden because the subclass redefines it with its own implementation. The crucial point here is that the method in the subclass must have the same name, return type, and parameters as the method in the superclass. This uniformity ensures that Java can correctly identify the overridden method. By overriding methods, subclasses can modify or extend the behavior of existing methods in the parent class. This is powerful because it allows objects to behave differently based on their actual type, even when they are referenced through a superclass type. This capability is what enables dynamic method dispatch, where the method that gets executed is determined at runtime, based on the actual type of the object, not the reference. In the context of the overall presentation, Understanding this concept is critical because it highlights how Java supports flexible and dynamic behavior in object-oriented programming. It emphasizes the importance of inheritance, method overriding, and runtime decision-making in creating robust, scalable applications. Priyanka Arunachalam here. Now, let's talk about compile-time polymorphism in Java, which is also known as static polymorphism or method overloading. This concept occurs when we have multiple methods within the same class that share the same name but differ in their parameters. Essentially, the method name stays the same, but the way they handle inputs varies. It's important to note that Java does not support operator overloading, so we focus solely on method overloading. Method overloading happens when there are multiple functions with identical names but different parameter lists. These differences can be in the number of arguments or the type of arguments. For example, you might have a method that adds 2 integers and another that adds 3 integers, all named add. By changing the number of parameters or the data types, Java can determine which method to execute at compile time, hence the term compile time or static polymorphism. This feature allows us to write more flexible and readable code, as the method name remains consistent while handling different types or amounts of data. And remember, this is different from operator overloading, which Java doesn't support. Instead, method overloading helps us achieve polymorphism through method signatures. Thanks so much for joining me today. I really appreciate your time and attention throughout this presentation. I want to especially thank Priyanka Arunachalam for her valuable contributions and support. As we wrap up, I hope you've gained some useful insights and are inspired to apply these ideas in your own work. Remember, the key takeaways are about innovation, collaboration, and continuous learning, concepts that are essential for success in our field. Once again, thank you all for being here. If you have any questions or want to discuss further, please feel free to reach out. I look forward to staying connected and exploring new opportunities together.